Hawaii is all about stunning landscapes full of rare species, jaw-dropping views, and beaches. In other words, paradise on Earth. Unless, of course, you're talking about the Big Island, the largest in the Hawaiian archipelago. For over 40 years now, its main resident has been Kilauea, a volcano that does nothing but pour out lava non-stop, sometimes so much that it leads to massive destruction. Can its force be stopped? Actually, yes, and the trick might be salt water. A huge amount of salt water. The idea sounds crazy, but it's not without reason, and you're about to see why. At the start of the 20th century, Kilauea began its destructive game. One of the most famous eruptions, which began in 1983, turned out to be one of the most devastating and longest-lasting in the volcano's modern history. Lava flows erupting from the side crater, Pu'au'au, moved slowly but relentlessly toward the coast, like a river of fire for decades. Naturally, they brought with them the destruction we've come to expect from volcanic eruptions. By 1990, for example, this fiery river had completely wiped out the small town of Kalapana. Over the years, the lava kept creeping over it and hardening. In the end, 189 homes, including a school and several historic buildings, ended up buried under layers ranging from 49 feet to 82 feet thick. The locals had no choice but to watch as their houses slowly disappeared, and along with them, the once picturesque shoreline vanished under black basalt. Lava flows also covered fertile farmland, leaving behind a barren, rocky wasteland. Yeah, the whole eruption started back in 1983, and its peak still wasn't reached, because the worst came in 2018. A volcano erupted a huge amount of lava from more than 24 new cracks and fissures that appeared in the Puna area, prompting the urgent evacuation of over 2,000 people. Lava flows destroyed more than 700 homes, turning thriving communities like Leilani Estates into a lava field littered with smoldering debris. Beyond destroying houses, the lava swallowed vital infrastructure too. Roads, power lines, and water systems, completely isolating some areas and cutting off essential connections between communities. The fire flow also reached and severely damaged what was supposed to get the power of the lava, Puna Geothermal Venture, Hawaii's largest geothermal facility, causing massive economic losses. The event became a stark reminder of how a single natural disaster can wipe out not just private property, but also key infrastructure. A unique feature of this eruption was that when the lava reached the ocean, it not only created a new stretch of land about 877 acres in size, but also completely reshaped the coastline, burying under it beaches, coves, and bays that had been favorite spots for locals and tourists. This served as a striking example of how geological processes can, in an instant, redraw a familiar landscape, replacing it with something new, alien, and unwelcoming. Besides that, the lava flows were so powerful and widespread that they completely filled Green Lake, which used to be one of the deepest lakes in Hawaii. The lava boiled away all its water, leaving behind just a solid black mass, forever destroying this natural feature. After that, there were no major or long-lasting eruptions, but as of 2025, the volcano's hazard level is set at watch, which means the volcano could erupt and there are signs of activity. So there's a chance the Big Island might see lava flows again. Maybe it's time to think about a strategy to pour salt water over all the current lava from Kilauea. And it's not just some fantasy. People have actually fought a volcanic eruption with seawater, and they succeeded. January 21st, 1973, Iceland, Hi'may Island. Nothing hinted at lava, or that millions of tons of water would be used to save the day. Yet that day, underground tremors began, which nobody took as anything unusual either. But then everyone realized a big problem was coming. On January 23rd, on the east side of the island, just 0.6 miles from the center of Hi'may town, a fissure started to open. It quickly grew from 980 feet at the start to nearly 1.8 miles long and split the island from one shore to the other. And on top of that, fountains of lava 164 to 492 feet high started shooting up along the entire length of the fissure. After that, a lava river formed, which began threatening both the town and the vital harbor, the main source of income and the only entry and exit point for the fishing community of 5,300 people. In the first weeks of the eruption, about 400 houses in the town were destroyed, some buried under lava, others damaged by tephra, that is, fragments of volcanic material tossed into the air during the eruption. Facing an even larger disaster, Icelandic engineers and locals decided on an unprecedented experiment with the goal of stopping the fiery force. The Icelanders knew they couldn't really stop lava, but they came up with a simple and bold idea. If you pour cold seawater on the front of a blazing flow, a solid crust would form on its surface. This crust acted like natural armor, slowing down the lava, and if cooled enough, it could even make the flow change direction. Essentially, the plan was not to fight the volcano head-on, but to build walls for the lava out of the lava itself, forcing it to go where it would be least dangerous. From the very beginning, the engineers knew that the key to saving the situation was how fast they could get the system up and running. Pipes were urgently shipped to the island, and over 7 miles of metal pipelines were stretched out to the lava front. They were laid straight over houses and streets, and in some places, even across lava that was still hot and solidifying. The system was anchored by 43 pumps arranged in several clusters to create maximum pressure. Within the first weeks, tons of cold seawater were dumped onto the lava. Hoses and hand lances blasted the hottest sections, where temperatures hit 1,832 degrees Fahrenheit, and every burst produced a hissing cloud of steam. The dredger Sandy played a key role, positioning itself right at the edge of the flow and pumping water for almost 2 weeks at a rate of around 105 gallons per second. It became the first water cannon against the Eldfell volcano. Streams of water hit the lava around the clock, cooling its surface and forming the first crusts. Later, when all the pumping units were up and running, the total system capacity rose to 264 gallons per second on the main front, with another 53 gallons of seawater per second flowing onto the lava on the northern side. At peak days, up to 43 pumping stations were active on the island, and all this equipment roared non-stop, sending water from the ocean straight into the heart of the fiery river. Between February and July 1973, this system ran non-stop, and the total amount of water poured onto the lava reached about 1.6 billion gallons. To put that in perspective, that's like thousands of Olympic swimming pools dumped onto volcanic rock. Water flowed through the pipes continuously, day and night, while workers were constantly fixing pipes and pumps damaged by heat and falling chunks of solidified lava. Sometimes they had to move the pipes because the lava burned the supports and flooded whole sections of the line. It all felt like a never-ending race. People moved the equipment almost as fast as the lava front advanced. By continuously pumping seawater, they managed to do something never done before. The lava front, which was about to seal off the harbor completely, was slowed and diverted. The flow stopped at just a few dozen feet from the port entrance, leaving the harbor functional. For the fishing town, where the harbor was the sole artery to the outside world and the foundation of its economy, this effectively meant saving the entire community. Without this effort, Iceland's primary fishing port could have been lost forever. But the impact didn't stop at just protecting the city. The lava flows, once solidified, formed new geological structures, massive walls of hardened basalt that acted as natural breakwaters. What's more, the eruption and cooling of the lava together created about 0.8 square miles of new land, expanding the island and strengthening the coastline. In a twist of irony, the disaster turned into an opportunity. The port, once at risk of destruction, gained extra protection from future storms and a stronger infrastructural base. You think that's it? Well, no, because people came up with a way to get even more use out of what happened. The locals drilled wells near the lava fields, from which hot steam kept rising for years. They decided to use it to heat houses and greenhouses. Now let's go back to Hawaii. Does it mean that the locals, particularly those on the Big Island, should start getting everything ready to protect all infrastructure during the next lava flow from Kilauea like they did in Iceland? Well, it's a great idea, but there are some issues. First of all, the scale. Jaime Island, where the 1973 eruption happened, is just a tiny piece of land about 5 square miles in size. Not much control was needed there, since the lava would just flow into the ocean on its own without spreading across large areas on land. Meanwhile, only a small harbor and the town needed protection from the lava's wrath. The Big Island isn't just a patch of land, it's the largest landmass in the Hawaiian archipelago, covering about 4,000 square miles, which makes it roughly 780 times bigger than Jaime. Sure, that doesn't mean lava from Kilauea can spread across the whole area, but you can definitely say there's way more room for lava flows from a Hawaiian volcano. Of course, there are some less important areas, and there's no point in defending them, yet the process still needs to be monitored more carefully because far more critical human infrastructure is at risk than it was in Iceland. What does all this mean? That the infrastructure to move water for dousing Kilauea's lava would have to be enormous, nothing like what they had in Iceland. If Iceland needed 7 miles of piping, Hawaii would need several hundred. Don't forget that keeping all this pipeline infrastructure running, especially when it's at risk of being destroyed by lava, takes a huge number of people. Overall, it sounds really complicated, and that's before we even get to the amount of seawater that would be needed to stop the lava flows. Look, in 1973, when the lava front and its volume were relatively small, it took a total of about 1.6 billion gallons of seawater, pumped using around 43 pumping stations. For Kilauea, where the lava front and the total lava volume were way bigger, you'd need over 100 such stations, and of course much more water. If you add the cost of the fuel required for the pumping stations, plus the cost for all the system's parts, it turns out that creating and maintaining such a system is almost physically impossible, and very costly too. And by the way, it's worth adding that cooling lava with seawater in Iceland and Hawaii is totally different in terms of cost effectiveness because the locations are very different in climate. In Iceland, the average yearly temperature is 34 to 41 degrees Fahrenheit, while Hawaii has a completely different climate with an average yearly temperature of 75 to 81 degrees Fahrenheit. Due to the laws of physics, cooling works better when the temperature difference between the lava and the environment is bigger. However, let's say there's unlimited money. After all, it's the infrastructure that needs saving. Hawaii throws every technical and human resource into building the system and even brings in other U.S. states. A perfect scenario where you could carry out even the biggest projects, right? Still, in that case, there's no way to stop a Kilauea eruption with salt water. On Jaime in 1973, lava flows stayed entirely on the surface, barely creating any subsurface channels. The lava was open and accessible, allowing engineers to deploy pipes and pumps to directly douse the leading edge of the flow with cold seawater. Everything was carried out on the surface, and getting to the lava was relatively easy, which made hands-on intervention actually possible. Unlike Jaime and Kilauea, lava flows very often travel through underground lava tubes, which are hidden channels beneath a solid crust. Lava inside these tubes moves quietly, staying liquid and flexible, while only a thin top layer is visible on the surface. This means that any attempts to interfere with the flow from above, like pouring water or building barriers, affect only the top layer, while most of the lava mass keeps moving inside the tubes, bypassing the obstacles. It should be noted that when lava hits seawater, it produces steam plumes filled with microscopic shards of volcanic glass and hydrochloric acid. These clouds can climb hundreds of feet high and spread for miles, making the air dangerous to breathe and eating away at equipment. Clouds like this were seen during the extinguishing of lava in Iceland, but on a much smaller scale than what might happen if you dump hundreds of thousands of gallons of water onto Kilauea's lava. In that case, the toxic releases would be a real hazard, even worse than what actually unfolded in 2018. At that time, since lava was hitting the ocean, huge clouds were produced. It's believed that this was one of the key reasons why the shoreline had to be evacuated. Being close to the lava-water contact zone was a matter of life and death. So another larger-scale example of mankind defeating a fierce force of nature with the help of seawater isn't likely to happen. But if everything falls into place, then it might be possible not only to hold back Kilauea's massive lava streams, but also to make use of them. For example, the Big Islands area could be expanded by directing all that lava into the ocean, just as it happened in Iceland. It should be noted that lava, even without any human intervention, poured out of Kilauea into the surrounding ocean in huge amounts. For instance, during the 2018 eruption in the Puna region, from 0.2 to 0.23 cubic miles of lava spilled into the sea, ultimately forming new deltas over 1.3 square miles in size and extending the island's coastline by roughly 1 mile. At the same time, if the flow could actually be managed, lava could be steered not just somewhere, but to a specific place that needs to be widened or restored after being damaged by erosion. Another way would be to do what the Icelanders did and tap into lava heat. That's an even more difficult task because in Hawaii, the situation is generally more complicated. Well, the large area, the powerful flows, you remember. Still, who knows? Maybe technologies will appear that make this possible. Besides, Kilauea holds a huge amount of energy. Even if you take just part of those 0.2 cubic miles of lava that poured into the ocean in 2018, you'd get an enormous amount of electricity. All in all, it all sounds good, but it never went as far as actually putting it into practice. Even just flooding it with seawater and thereby redirecting the lava from the Big Island's infrastructure somewhere else is an impossible task because of the sheer scale and other specifics of Kilauea's eruptions. Actually, it's pretty sad, because eruptions with lava flows aren't the worst thing volcanoes can unleash. In Italy, there's Campi Flegrei, or the Phlegraean Fields, a true giant among Earth's supervolcanoes, sitting just a few miles away from bustling historic Naples. Its caldera stretches 7 miles across, looking like a massive cauldron that once held an incredible amount of magma, powerful enough to change the climate across vast regions. This volcano was formed as a result of a series of massive eruptions, one of which took place about 39,000 years ago, leaving behind consequences that, according to scientists, may have triggered a sharp cooling and even played a role in the extinction of the Neanderthals. Modern science is still studying its complex network of underground magma chambers in an attempt to understand what forces are hidden beneath the surface. Today, volcanologists are keeping an unusually close eye on Campi Flegrei since the volcano is showing alarming signs of activity, forcing specialists to carefully study every shake and shift in the ground. In recent months, more than 3,000 subterranean shocks have been detected, including a strong 4.4 magnitude earthquake, the biggest in 4 decades. Meanwhile, the slow uplift of the caldera's surface points to magma still creeping slowly but surely beneath the Earth. Meanwhile, gases like carbon dioxide and hydrogen sulfide are being released, pointing to rising pressure in the magma chambers. This makes forecasting extremely difficult, as even a small shift in pressure or temperature might spark sudden activity. Should the Phlegrean fields actually wake up and erupt, the impact would be severe. Experts estimate the volcano could eject roughly 0.23 to 0.7 cubic miles of magma. Sure, that doesn't sound too disastrous, but Campi Flegrei worries scientists for other reasons. During its eruption 39,000 years ago, the volcano threw out about 48 cubic miles of pyroclastic material. To put that in perspective, the famous Vesuvius only released around 1 cubic mile. Besides that, if Campi Flegrei erupts, it could throw ash tens of miles into the atmosphere. At the same time, the coverage area could reach hundreds of square miles, especially in southern Italy, and that would only cause local effects. But if the super eruption scenario comes true, the ash could affect Europe's climate for several months, dropping the temperature by 1.8 to 3.6 degrees Fahrenheit. It should also be said that if Campi Flegrei erupts, scientists predict it could release tens of millions of tons of carbon dioxide and hydrogen sulfide in just a few days. At the same time, it's quite likely that this would trigger acid rains and aerosols, which reflect sunlight and affect the climate. We think it goes without saying why this would be a disaster for the local population, as well as for many people in other European countries. And while at least we have a rough idea of what can be done with flowing eruptions, with an event like this, which is far more dangerous, we really have no clue at all. Still, scientists are working on it, which is good news for people living near such volcanoes, which could one day erupt and turn into a disaster. One of the most promising ways to monitor volcanic activity is using thermal data collected from the International Space Station. Studies carried out by the National Institute of Geophysics and Volcanology have shown that analyzing thermal images from the ISS makes it possible to spot significant temperature changes that happen before strong earthquakes in the Campi Flegrei area. A great solution is it allows for early warnings about possible seismic events, which is especially important when densely populated areas happen to be near volcanoes. Another major achievement in science is the use of drones equipped with tiny gas sensors and spectrometers. These devices make it possible to safely and efficiently gather data on the composition of gases and volcanic emissions, even in hard-to-reach and dangerous areas. Cambridge University's Aerial-Based Observations of Volcanic Emissions project has successfully used this technology to study active volcanoes like Manam in Papua New Guinea. The drones are equipped with sensors that can measure carbon dioxide, sulfur dioxide, and other gases, allowing scientists to more accurately assess a volcano's activity and predict possible eruptions. Significant progress has been made in the field of data processing with the introduction of machine learning methods. The developed approach analyzes 4 key seismic indicators, creating a probabilistic tool for real-time use that can give early warnings hours or even days before a potential eruption. Naturally, this approach allows for a significant improvement in predicting volcanic activity and timely informing the population about possible threats. Moreover, using distributed acoustic sensing with fiber optic cables opens up new possibilities for monitoring volcanic activity. This technology allows detecting seismic signals that traditional sensors might miss, giving a more complete picture of what's going on. The technology is already being successfully used to monitor volcanic activity on Etna, providing detailed data on seismic events, including explosions and degassing. Using fiber optic cables makes it possible to build more reliable and long-lasting monitoring systems that can operate in high-temperature and harsh chemical environments. These innovative methods significantly improve the accuracy and timeliness of predicting volcanic activity, which in turn helps enhance early warning systems and reduce risks for the population. Using a mix of technologies like thermal monitoring, drone studies, machine learning, and distributed acoustic sensing allows scientists to track changes in volcanic activity more effectively and take timely action to protect people and infrastructure. For now, this is the only way to survive big volcanic eruptions. Still, Iceland has taught us a lesson, and even if technology lets us down, vast amounts of seawater can save countless lives.